Hello everyone, this is Manohar Reddy, Assistant Professor, Department of Cybersecurity, Institute of Aeronautical Engineering College. Today I am going to discuss about the next concept, Stochastic Process Markov Chain Theorem. Stochastic Process Markov Chain Theorem. It is simply called as Markov Chain Random Process Theorem also. It is simply called as Markov Chain Random Process Theorem also. So we will see how it works for the random variables and the random elements. So stochastic process Markov chains. Stochastic process Markov chains. So a Markov chain or Markov process is a stochastic model. That is nothing but a random model describing a sequence of possible events. Describing as sequence of possible events. Sequence of possible means the number of ways that are possible events. The sequence of possible events in which the probability of each event depends only on the state attained in the previous event. That means the sequence of the event is depending on the previous event. So that events are depending on one to another. So the previous event is depending for the next event, or next event is depending on further coming events. So that is what we mentioned here. So a Markov chain or Markov process is a random model or stochastic model for describing the sequence of possible events in which the probability of each event depends only on the state attained in the previous event. So there are two types of process are there. So we already discussed in the random process. One is discrete time random process and second one is continuous time random process. So that is what we mentioned here, the countable infinite sequence in which the chain moves the state at discrete time steps. The chain moves a state at a discrete time steps gives a discrete time Markov chain process, and a continuous time process is called as a continuous time Markov chain process. So in probability theory, Markov model is a stochastic model used to model randomly changing the systems over time. So it is a model randomly changing systems over time. So for example, the amount of money the gambler possesses after toss T. The amount of money the gambler possesses after toss T. So after tossing the coin, will say that the money of the gambling, right? So and the number of students enter in a class before time T. The number of students enter in a class before time T for the day 1 to day 10. So for the day 1, the 8 members are coming at regularly. For the day 2, 10 members. But we are not going to find the exact time for the exact members, right? Exact time for the exact members. So to do all the process, we are going to use this stochastic random process, that is Markov chain or random process. So see here how we are going to define the stochastic process. So let xn is the member of the event. So any of the member of the event that where n equals to 0, 1 to 0, 1 or 2 be a stochastic process that takes on a finite or countable number of possible values. So here we'll see for the n equals to 0. So x0 be the number of students entered in class at t equals to time 0. T equals to t0. So at this point of time, x0 be the number of students entered in the class. At what time? So 8 p.m. So here you can take like 8 members. So 8 members entered in the class time 8 o'clock. Similarly here you can see 9 members entered in the class time 9 p.m. up to like that. So n member of the students are entered in the time at tn, entered in the time at tn. So these all are the events of the sample space. So let xn comma n equals to 0 1 2 be a stochastic process, that is all random process, that is all random process that takes on a finite or countable number of possible values, countable or finite number of values. So from the above we observed that xn equals to I. From this above xn equals to I, so it means is said to be the in state I at a time n. So it is in state of I and it is in state of the I at a time n, at a time n. So at particular time, at particular time the student is getting present, at particular time the student is getting absent. So that is what we mentioned here, the state and the time, right? So from this we are going to say that a Markov model, two terms plays an important role. A Markov model, a Markov Chains stochastic process or that model process, two terms a very important role. So one is state and second one is transition probability. One is state and the second one is transition probability. State represent current situation or current functioning of the event. So current state of the event or current functioning of the event. So we'll coming to this example. So the weather, if you take an example of the weather, so raining today is one state, raining today is one state, and non-raining today is all another state. Raining today is one state and not raining is another state. So you can say that today may be raining, today may not be raining. So today may be raining or today may not be raining. Similarly, if you can take for the student also, the student may be present, a student may be present in the college or student may be absent in the college. So these two are said to be the states. These two are said to be the states of the event student. Event student. Similarly, here we are seeing that weather, for the weather report, so the raining today is one state and non-raining is also another state, right? So these are the two states. So that is about one state. And see here, if if you are taking today present state, if you are taking the present state is what raining today, and for this raining today, for the today state, what we are going to expect on tomorrow, what we are going to expect on tomorrow. So if the state is raining today, then we can assume that tomorrow is also raining, and you can also assume that tomorrow is no rain, tomorrow is no rain. For this state, we are going to assume these two states for the tomorrow, these two states for the tomorrow. So these two are nothing but transitions, we can say that, transition, we can say that. And if we'll take not rain today state, if we'll take not raining today state, we can assume that tomorrow may be raining, tomorrow may not be raining, tomorrow may be raining or tomorrow may not be raining. So taking these two states as a rain today and a not rain today, for these two states, for the tomorrow positions also, there may be a chance to getting rain for the tomorrow and there may be not chance to getting rain. So that means no rain. So for the rain state today and for the not rains today, we'll have this all the states for tomorrow, right? So we can assume that today's state will become as the same state for the tomorrow or may not be the same state for the tomorrow. So like the way you can understand these two states, right? And from this you can see, you can observe that transition also. So from this transition probability is there, right? So one is a state and the second one is the transition probabilities. See here the probabilities of the states. If raining is today, if the raining is today, what will be the assuming probability for the tomorrow? So we can assume that 40% of the chance getting rain for tomorrow, 40% of the chance to getting rain for tomorrow, and the remaining 60% of the chance may not be coming rain tomorrow. These two will happen for this state today. These two transitions will happen for this rain today state, and similarly you can go for the not raining today state. So for the not raining state, we can assume that 70% of the 70% of the state is going to be rain for tomorrow, and remaining 30% is not a rain for the tomorrow state, not rain for the tomorrow state. So based on these states and assumptions of the probabilities of the states, we can draw the transition diagram. We can draw the transition diagram that represents the transition probability diagram. That represent transition probability diagram. So see here, we'll have to draw these states. One is rain state, and the second one is not rain state. Not rain state. So these two are the states, and these two are the states for coming days. That is next day, the chances of the rain for getting rain, and the chances of the not getting rain. So what is the probabilities? So if today is rain, and if tomorrow is also rain, then you can have the probability 40%. You can have the probability 40%. This is the transition. This is the transition. You can say that this is the transition. And similarly for the not rain for the tomorrow means you can have the 60%. 60% of the state, you can say that tomorrow is not raining. This is the for this rain state. And for also not rain state, so if you'll take not rain state, the tomorrow is not raining as 30% probability, and rain tomorrow is 70% probability. So that means these are all, you can say that, probabilities for the states for tomorrow decisions, and the probabilities for the states today decisions. So today decision probability and tomorrow decision probability. So these all the diagrams, you can say that transition diagram. This all the diagram, you can say that transition diagram. So these are all the transition diagram contains states, contains transitions, contains states, and contains transitions along with the transition probabilities. So this is the diagram. You have to draw the states along with their probabilities. This is the transition diagram. We have to draw the states and along with the probabilities, right? So we'll see. So representation of model and matrix, representation of transition model and matrix. So coming to take these two states, rain and not rain, for the today, and we'll see all these transition probabilities for the tomorrow decisions, having this 0.6 probability of rain state to not rain state for the tomorrow, and similarly rain state to tomorrow is also rain state to 0.4 probability, and not rain to rain state is 0.3 probability, and not rain to not rain or tomorrow also 0.7 probability. So now based on this diagram, based on this representation model, we have to draw the matrix that is called as a transition matrix. So we have to draw the matrix that is called as a transition matrix. So we'll see for the today state rain, and we can assume that today states rain and not rain. These two are today states, right? And tomorrow states also, there may be a chance to occur rain, and there may not be chance to occur no rain. So what is the probability? So rain to rain. So rain to rain probability is 0.4, and rain to not rain probability is 0.6, and not rain to rain probability is 0.3, and not rain to not rain probability is 0.7. So like the way you can take the states and you can take the probability values, and with that states and transition probability values, you are going to construct the matrix. That matrix is called as transition matrix. That matrix is called as transition matrix. So transition matrix, always matrix represents rows and columns, right? So that rows and columns are represents here states for today and states for tomorrow decisions. So states for today, rain and no rain, and for the tomorrow also rain and no rain. And what is the probabilities for that rain to rain and rain to not rain? So we have to construct this matrix with the help of these states and transitions. So after constructing this matrix, you can say that this 0.4, 0.6, 0.3, 0.7 are the probabilities for the today's states on behalf of next day decisions. Next day decisions. So this is the way you can represent the transition diagram, and from the transition diagram you are going to construct the transition matrix also. Transition matrix also. See here, the Markov chain is the process which contain x0, x1, x2 up to xn. Here, the states are observable and fully autonomous. The states are observable and fully autonomous. That means you can change that state accordingly your interest. So, the simplest of all Markov models states that the state of Markov chain at a time t is the value of xt. So, for example, xt equals to 5. This is the we say that the process in state 5 at a time t. So this means it indicates that it is in fifth state or it is in state at 5 with the time t. The state at 5 and the time t. It is going to show that like. And Markov property are memoryless. So what are the property of Markov? So the basic property of the Markov chain is that so the time which comes for the next sequence, that is nothing but xt plus 1. xt plus 1 depends upon xt. That means directly we are saying that the future situation is depending upon present situation. The future situation is depending upon present situation, but it does not depend on past situation. That is nothing but xt minus 1, xt minus 2 up to x1 comma x0. So the basic property is what Markov property states that the future states or depends on present states but not past states. So mathematically it represents like the Markov property is stated as p of xt plus 1 equals to j, xt equals to I, xt minus 1 equals to I1 up to x0 equals to I0. So that is depending upon only the present state, right? So the future state xt plus 1 is depending on present state xt, but not on xt minus 1 equals to I1. But not on xt minus 1. That is, xt minus 1 is past state. Xt is present state. Xt plus 1 is future state. So Markov property or memoryless property states that I am not going to depending upon past state. I am just depending upon present state. I am the future state and I am the future state. I am going to depending upon present state but not past states. So that is what the Markov property tells that. Right. So for t equals to 1, 2, 3 up to all for states, all for the different states. And see the transition probabilities. So we already seen that the transition probabilities represents with the states, right? Represents with the states along with their probabilities. So there are two types of probabilities. One is the transition probability. Second one is n-step probabilities. One is transition probabilities and the second one is n-step probabilities. So we'll see what is the difference between transition probability and the n-step. So one step is this is one step and this is n-step probability. So see here, probabilities from state I to state j after one step time period. After only one step time period, that is denoted by Pij. That is denoted by Pij is defined as Pij equals to P of xn plus 1 equals to j, xn equals to j. P of xn plus 1 equals to j, xn equals to I. Xn equals to I. So examples what? X2 equals to 3, X1 equals to 2. So that represents 2 to 3 state. That represents 2 to 3 state. So P of 2, 3 is the state. And similarly, P of X2 equals to 2 and X1 equals to 0. So 0 to 2 state. 0 to 2 state. So P02. P02. So this is all, you can say that it is only one step probability. So only one step probability. And while coming to the n step probabilities, the probabilities from state I to state j, state I to state j after n step time period, not one step, n step time period. If you take time period 2 minutes or 3 minutes, it will shows there are 2 step period or 3 step period. So it is denoted by Pij of n or Pij of n. Pij of n is defined as Pij of n equals to P of xn plus 1 equals to j, x1 equals to I. So xn plus 1 equals to j, x1 equals to I. Consider this example. So P of x2 equals to 3, x0 equals to 2. Then P of 2 to 3 state, P of 2 to 3 state is the 2 minus 0. 2 minus 0, that is nothing but 2. The value is 2. Similarly, for the P of x3 equals to 2, x1 equals to 1. So 1 to 2 state, 1 to 2 state, P of 1 to 2 state, the difference is 3 minus 1, that is 2. P of 3 minus 1, that is 2. That means P of 1 to 2, the memoryless property says that 2 value, and P of 2 to 3, the memoryless state that 2 value. So that is the way you can understand the difference between transition probabilities, one step probability and n step probability. So one step probability is nothing but one step time period it is denoted, and the n step probability is nothing but n step time period it is denoting. N step time period it is denoting, right? So that is about n step and transition probabilities. And next, see here the example transition diagram. So these are all the 1, 1, 2, 3, 4, 5, 6. These are all the states. These are all the states that can have the futures as well as present. That can have the future states as well as present state. And the probabilities 0.4, 0.5, 0.3. These are all the different types of probabilities. These are all different types of probabilities. These are all the different types of probabilities. So from these all the probabilities, so we are going to find the values like P of x3 equals to 6, x2 equals to 4, x1 equals to 2, x0 equals to 5, x3 equals to 6, x2 equals to 4. So this you can simply it as, you can rewrite it as P of x3 equals to 6, x2 equals to 4. P of x3 equals to 6 and x2 equals to 4, because x1 equals to 2, x0 equals to 5 are not dependent, not dependents. So we can rewrite it as simply P of x3 equals to 6 and x2 equals to 4, right? So this is all about this diagram. So these are all represents transitions probabilities. These are all represents transitions. You can write it as transitions, right? And these are all states. And these are all probability values. Probability values. That is nothing but transition probability values. Transition probability values. Right? See the transition probability matrix. So from these all the transition probabilities, we are going to form a transition probability matrix. So the matrix describing the Markov chain is called as transition matrix. The matrix describing the Markov chain is called as a transition matrix. That is nothing but transition probability matrix. Transition probability matrix. While we constructing this transition probability matrix, we need to remember some key points. We need to remember some key points like this. So what? we have to remind this. Rows always represents now or from or present. So rows always represents now or from or present. So whatever the state you are going to represent, it is in rows wise. And the columns represents always represents next to or future, next state or to state or future state. So it is going to represent column always represents. So and entry of I comma j is the conditional probability. Entry of I comma j is the conditional probability that the next state equals to j, given that now equals to I. That means the present state is I and the next state is j. So I to j. In other words, the probability of going from state to I state, from I state to j state. So I to j, that is nothing but from this state to the next state. So that is what we have to remember this all the points. We have to remember this all the points while we constructing this all the transition probability matrix. So transition probability matrix P11, P12 up to P1n. So this is the first one and this is the second one up to Pn1. So these are all represents rows and these are all represents columns, right? So based on that only we are going to construct the transition probability matrix. So transition probability matrix contains all the states and the transitions along with the probability values. So this all the states and the transition probabilities contains what? The rows and the columns of this matrix. So this matrix is said to be transition probability matrix if it must be square matrix and if the Pij greater than or equals to 0 for all I and j, and sigma Pij equals to 1 is a row wise. So this is all we have to remember. These are all the points. And we'll see. Consider the Markov chain with 3 states. We have 3 states here. One problem. Consider this Markov chain with 3 states. S equals to 1, 2, 3. That has the following transition matrix. So they are given a transition matrix. So we are given transition matrix. Along with this transition matrix, what we need to do? So draw the state transition diagram for this chain. And if we know P of x1 equals to 1 equals to P of x1 equals to 2 equals to 1 by 4, then find out the P of x1 equals to 3. Find out the P of x1 equals to 3 as well as P of x2 equals to 2 as well as P of x3 equals to 1. So these things we need to find out. So first of all, the state transition diagram as shown in figure. So with these values, these are all P of 1, P of 1, 2, P of 1, 3, and P of 2, 1, P of 2, 2, P of 2, 3, and this one P of 3, 1, P of 3, 2, P of 3, 3, right? So with this all the transition probability matrix values, we are going to construct a transition diagram. So total how many states are there? We are having 3 states. S equals to 1, 2, 3. So S equals to 1, 2, 3 states. So we are going to construct a transition diagram with these 3 states. So one state, second state, and third state. So taking these 3 states and P of 1 to 1. So P of 1 to 1, what is the value? 1 by 2. P of 1 to 1, 1 by 2. And P of 1 to 2. So P of 1 to 2, what is the value? 1 by 4. And P of 1 to 3. So P of 1 to 3, what is the value? 1 by 4. Similarly, P of 2 to 1. The value is what? 1 by 3. Similarly, P of 2 to 2. P of 2 to 2 is 0. So there is no loop. So you can don't write this one. And similarly, P of 2 to 3. So P of 2 to 3 is what? 2 by 3. P of 2 to 3 is what? 2 by 3 value. And next, P of 3 to 1. So P of 3 to 1, the value is 1 by 2. and next P of 3 to 2. So P of 3 to 2, the value is 1 by 2. The value is 1 by 2. And next P of 3 to 3, we are not having any loop, so it is 0. So we don't want to write it. So P of 3 to 3 is 0. P of 3 to 3 is 0. So with this, all the transition probability matrix values, we have to draw the diagram like this. You have to draw the diagram like this. After drawing this all the diagram with the help of states and with the help of transition probabilities. So this 1, 2, 3 states, these 3 are states and these all are transitions. These are all are transitions, right? So with the help of these states and the transitions, we have to draw this diagram. So after drawing this diagram, what we need to get? We know P of x1 equals to 1 equals to P of x1 equals to 2. That means the probability of occurring x1 equals to 1. The probability of occurring x1 equals to 2, the value is 1 by 4. But we need to find out what P of x1 equals to 3. We need to get, and x2 equals to 2 we need to get, and x3 equals to 1 we need to get. So we need to find the values of this one. So P of x1 equals to 3 at the moment, and P of x2 equals to 2 at the moment, and P of x3 equals to 1 at the moment. So we'll see. So first we obtain P of x1 equals to 3. We need to obtain P of x1 equals to 3. So how we are going to get P of x1 equals to 3 means the value is 1 minus P of x1 equals to 1 minus P of x1 equals to 2. We already know these two values, right? We already know these two values from this here. P of x1 equals to 1, P of x1 equals to 2. That is what? 1 by 4. So 1 minus 1 by 4 minus 1 by 4. So 1 minus 1 by 4 minus 1 by 4 is nothing but, you can write it as 4 minus 2 by 4. That is nothing but 2 by 4. That is nothing but 1 by 2. So now we got P of x1 equals to 3. We got P of x1 equal to 3. So that is what we need to find first. P of x1 equals to 3. Right. So after that, what we need to do? P of x1 equals to 3, P of x2 equals to 2, x3 equals to 1. So this is what we need to find out. So P of x1 equals to 3 we already get right now, and P of 3 to 2. So P of 3 to 2, P of 2 to 1. So x2 equals to 2 means at the state of x2, this 2 to 2. 2 to 2 means 0, and 2 to 3 is nothing but 1 by 2. So 2 to 3 is nothing but 1 by 2. Similarly 2 to 1. So 2 to 1 is nothing but 1 by 3. So you can write 1 by 3. 2 to 3 and 2 to 1, 1 by 2 and 1 by 3. So P of x1 equals to 3 is what? 1 by 2. So substitute this all the values, 1 by 2 into 1 by 2 into and 1 by 3. 1 by 2 into 1 by 2 into 1 by 3. That is nothing but 1 by 12 value. 1 by 12 value. So this is the way you can obtain the values from the transition diagram as well as transition probability matrix. Right, transition probability matrix. So this is all about transition probability matrix. So see here, the diagram represents all the transition probabilities along with the states. So along with the states and the transition probabilities, we have to draw the transition diagram, and then next we have to find the transition probability values for the particular states. So this is the way you can understand the problem, right? So thank you all.
Like, share and subscribe. Hit the bell icon for more updates.